We do have a lot to cover actually today, and I don't think we're going to get to the end of all of these different execution models. But you're already familiar with Dataflow, so we're going to flow very fast while covering Dataflow. I guess before we get started, you all know that homework 3 is due February 25th, and lab assignment 3 is also due. Well, not on the same date though, March 1st. That's the end of next week. So hopefully you're, who finished this lab assignment? Almost, that's good. So now you know where you should be perhaps. No, as long as you finish it on time, it's fine. But hopefully, I'd encourage everyone to participate in this extra credit assignment again. We would like to get the lowest execution time. Yes?
You happen to know like a ballpark for what we would need to get extra credit, like from last year or something?
Oh, you can check last year's slides. And maybe we can post it. I think the assignment is different from last year, so I don't think it'll be a perfect example, but you can see at least. And Jason can tell you more. Jason was the winner of last year, I think. Who's your TA? Yes?
What exactly does lowest execution time mean?
Lowest execution time. So what exactly that means, that will be dependent on the workloads we test your code with.
So is it simulation time or clock cycle time?
It's the execution time. Remember execution time? Number of instructions times IPC times clock cycle time. So it's the entire execution time in terms of nanoseconds of a program.
So pretty much the execution time if this implementation was to be filed.
Oh, that's right. Yes, that's right. Exactly. Yeah. Since you're not going to build the processor, it's the execution time over simulation. You're right. After we simulate your processor. Okay. So it should be fun. And you can test your programs also. You can test your design with different kinds of programs, right? Because you don't know what program we're going to test it with. We're going to test it with a bunch of programs. And Jason's over there, so you can ask your question to him after lecture. Okay, course feedback sheet. I do still want this. So if you haven't turned it in, please do so. It was due February 15th, but this is an assignment where I will accept late homeworks. This is important. A little bit on the course before we move on. Some of you had the feedback there are a lot of lectures. Yes, there are a lot of lectures, but as I told you earlier, we'll reduce the lectures later on, unless you don't want us to, of course, so that you can focus on the harder programming assignments. And we are actually running ahead of the programming assignment. I realize that. Hopefully you won't forget what we covered in the lecture before you start the programming assignments. But the goal is to have fewer lectures toward the end of the semester, such that you can focus on the harder programming assignments. And we will still have recitations toward the end of the semester, so you will still be able to ask questions on your programming assignments and everything else. But we do still want your feedback. Okay, readings for today. Hopefully we'll get to the GPUs, but I'll give you the basics that are required to understand the GPUs today, which is essentially vector processing or single instruction multiple data processing. And hopefully you'll see that existing GPUs are really not that much different from vector processors of old times, with a very, very key difference, which is the programming model. But we'll get to that. And this paper talks about that programming model difference nicely. And this paper is a general overview paper as well that talks about GPUs. And next week, we'll cover virtual memory. And hopefully you'll do these readings. You're already familiar with the concept, but we'll cover how hardware and software cooperate together to enable a view to the programmer that shows infinite memory, or that gives the illusion of infinite memory to the programmer, as well as some other things that are attached to virtual memory, like protection. But this should be fun. You've seen virtual memory from the more or less software perspective in 213, right? But you didn't go into details of how you accelerate it in hardware. So you can imagine virtual memory purely being in software. If there's no hardware component of virtual memory that accelerates it, like the translation look-aside buffers, it'll run like a dog. So you don't want infinite memory if your memory is taking 200 cycles to access just because you need to do translation every single time, which also goes through memory. Right? So you want some acceleration. And that's the hardware acceleration part of virtual memory is where we will focus on. But we will focus on the entire system, too. OK, so do the readings. Last lecture, we've covered out-of-order execution. We're almost done. We covered Thomas Low's algorithm and went through an example in detail. We talked about out-of-order execution as restricted data flow execution. So hopefully you remember all of that. And it's restricted in two ways, right? It's restricted in, the first way is obvious. We're obviously not using a data flow ISA, right? The ISA is sequential, one Neumann model. Underneath, we're doing out-of-order execution. So it's restricted to the microarchitecture level. The second reason it's restricted is because it's looking at a window, right? And that window is really the instruction window. The instructions that are decoded but not yet committed to the architectural state form your instruction window in an out-of-order execution engine. And the data flow graph that you build dynamically and implicitly in the out-of-order engine is restricted to that window. So you remember the examples, and I'll flash through them at some point today. So today, we're going to wrap up out-of-order execution, talk about memory dependence handling and alternative designs. Oh, this didn't come out. This might be a PowerPoint bug, but that's OK. And we're going to go into alternative models. But let's cover out-of-order execution. Let's finish it first. I'm going to flash these. We talked about out-of-order execution with precise exceptions. You remember the two humps in the pipeline. The pipeline is in order until instructions are put into the reservation stations. Then everything is out of order. Scheduling is out of order. And the pipeline, again, becomes in order. You reorder the instructions to commit to the architectural state in program order. And you know how to do this. Basically, there are four things that enable out-of-order execution: linking the consumers of a value to the producer via register renaming, buffering instructions until they're ready via reservation stations, keeping track of readiness of source values of an instruction by broadcasting the tag and comparing the tags with the source tags, and waking up and selecting or scheduling the instruction when all source values of an instruction are ready. And this is another way of looking at it, so I'll flash this again. And we finished at registers versus memory. Remember, there's a fundamental difference between registers versus memory, and you know the three reasons, three fundamental differences. I've covered this several times. I'll flash it again. Register dependence is known statically. State is small. So register state is not visible to other processors. Right? And this leads to how we handle memory dependencies differently. OK, the problem that I left you with is memory address is not known until a load or store executes. Right? But we need to obey memory dependencies in an out-of-order machine. And it may be that you have a load instruction whose address becomes ready. So it's ready to execute. But there are store instructions with unknown addresses that are older in the machine. Then the question is, what do you do? Right. And we talked about three different ways. Conservative handling, well, I guess it's not here, but you can read this, basically. This is a memory dependence handling. You need to handle this. We talked about three different ways of doing this. Conservative way is stalling the load until all of these have known addresses. Then you can compare the addresses and say, I'm not dependent on any store. Or maybe if there's a store that's dependent, it's, this load gets the data from that store. Think about that logic now. We'll get to that in a little bit. Aggressive way, when the load address becomes ready, you assume the load is independent of any of the an unknown address store and schedule the load right away. And an intelligent way, you predict whether or not the load is dependent. And even more intelligent way, you predict which store the load is dependent on, right? So that you can get the value directly almost. Actually, another thing to consider is store has an address and a data value, right? These could be available at different times because they may be depend on different operations. Right? We're doing out-of-order execution, right? This may be unknown, but this may be known. So if you actually can predict this load is dependent on this store, even if the store address is unknown, and if you predict it correctly, you can supply the data directly. Right? But think about the logic that's required for this. And existing processors actually have this kind of logic. It's complicated, right? It's actually a little bit more complicated than you might imagine because there are other issues involved in it. But maybe we'll talk about that. OK, so this is the problem. There are two key issues. One is, how does the out-of-order engine detect dependence of a load instruction on a previous store? And the other is, how does the out-of-order engine treat the scheduling of that load instruction with respect to previous stores? So there are actually two options. One is the cheapest option. When you get this load instruction, and regardless of whether or not you know the address, you wait until all previous stores are committed. Right? In this case, you don't need even something called a store buffer. Right? This is a dumb option, if you will. Right? Because you're now really serializing stores and loads. To execute this load, you're waiting until all stores in the machine are done, committed. This way, you don't even need to check the address, right? That's the simplest way. But it's very low performance. You don't want to do this. Because think about it. If you have, let's say, 20% stores in your program and 30% loads, now 50% of your instructions, you're really serializing them. And you're, in fact, waiting until these instructions are committed. And you have to commit the stores in order anyway, right? You don't want to commit the stores out of order. Because what might happen is there might be an exception in the middle, right? And if you commit it out of order, now you're not obeying precise exceptions. OK, the other option which existing processors employ is they keep a list of pending stores in what is called a store buffer, and they check whether the load address actually matches the store address. So you can imagine a store buffer. It's really no different from the reorder buffer, actually, but it's a smaller buffer that keeps an age-ordered list of stores. This is the oldest store in the machine. This is the youngest store. And you have a valid bit and an address, and then address valid bit. This is entry valid bit. And then data and a data valid bit. Make sense? And actually, you need to have more. And that will become clear soon. What else do you need to have? Any guesses? I'll call this the INUM, instruction sequence number, right? You will need this because you need to figure out whether this load actually is younger than a store, right? When you do the search. You actually need something else, which is the size of the store. Now it's becoming more complicated. Because a store can be 1 byte, 2 bytes, 4 bytes, ... depending on your ISA, right? OK. So basically, you have this list. Now you know all the stores in the machine. And when a load generates its address, you can check this to see if the load is actually dependent or independent of any of the stores. How do you do that? This load's address comes in, and you have the address. Address is here. Address valid means whether the address is actually available or address ready. We can change this to ready, and the data ready. You take this address, compare it to every single address in the store buffer that is actually a valid entry, and the address is valid. But this is not that simple, because there may be multiple stores with the same address, but you want the instruction, you want the store, you want to only search the stores that are older than this load, right? So you need to check if the store's instruction number is actually smaller. Sequence number is smaller than the load's instruction number. So you actually do a search on the instruction number as well. So this CAM is becoming more complicated, right? I mean, you can simplify this, but this is conceptually a CAM, content addressable memory, right? And you also need to check if the size overlaps, right? Because what you really have is the store's beginning address and the store's ending address, depending on the size. And load also has a beginning address and a size, right? Ending address. So what you're really checking is if this store that's doing a store from this address to this address overlaps with this load that's doing a load from this address to this address. And if there's any overlap, then you need to wait. Then you're dependent. It could be, for example, you're doing a store of 4 bytes, and you're loading 1 byte, and there's overlap in that byte. Especially this becomes complicated if you have unaligned stores and loads, right? So now you can see how complicated this is getting. Maybe we'll let you design it in one of the labs. Somebody wants an out-of-order execution lab, I think. Yeah. So you'll need to build something like this if you. Of course, you can handle it this way, but then your out-of-order processor will have terrible performance. Okay. So this is essentially the store buffer, and this is the load store dependency check logic. Now, once you can figure out the dependency of a load on a previous store, what do? That's another question, right? This is just to figure out the dependency. You can, by doing the search, this is essentially an age-ordered search, right? Age-ordered search on an address range. The input is an address range, and you check if that address range matches any of the older address ranges of any store. Once you figure out whether there's a match, but it's not that perfect because there may be unknown addresses also, right? If there's an unknown address, you have no clue whether the address range matches. Okay, so how do you, you get all that information, what do? You can assume load is dependent on all previous stores if there is actually an unknown address. If there's a known address, there's no problem, right? If you actually know that there's a store, basically if you know that the store is actually going to produce the data for this load, then there's no problem. Once you do this dependency check, you can actually even supply the data from the store buffer. This is called store forwarding, store data forwarding. Basically, you don't wait until the store actually writes the data into the data cache, which will happen when the store actually commits, gets out of the machine. But when you do this dependency check, when a load searches the store buffer and finds if store is actually going to produce that data, it basically gets the data out of the store buffer, assuming the data is ready. Right? That's called store data forwarding. And it's the same as forwarding from another functional unit, right? You can think of stores operating on a functional unit and loads operating on another functional unit. You're basically forwarding from the store's functional unit to the load's functional unit. That's what's happening here. Okay, so if you know the address, there's no problem. If you know basically who is the producer of the value that you're going to get. But if you do not know the address, now you have these 3 options that we discussed, right? You can have the conservative option. You can assume the load is dependent on all stores that have an unknown address. You can assume load is independent, or you can predict the dependence of a load on an outstanding store. Let's take a look at the upsides and downsides of these options. If you do the first one, the conservative one, it's nice because there's no need for recovery, right? You wait for all addresses to become available. But it's too conservative. It delays independent loads unnecessarily. And it turns out most of the loads are actually independent of the previous stores. This is empirical data. And you can imagine the reasons, right? You can assume load is independent of all previous stores. This is very aggressive. This is simple because you don't need a prediction mechanism like you have in option 3, and can be common case. In this case, there's no delay for independent loads, right? If the load is actually independent, you just execute it right away when its address becomes available, which is nice. The problem is if you're wrong, now you require recovery and re-execution of the load and the dependence or everything that comes after it. Right. So it's the same as a branch misprediction recovery. It's a value misprediction recovery, similar, right? Because you get the wrong value if this is the case. You load from the data cache, whereas you should have actually gotten from the store. Option 3 is the prediction. And it turns out this is actually more accurate. It turns out people have showed that dependencies between stores and loads are relatively predictable in many cases. That's the upside. So you get better accuracy. You don't do this aggressive prediction, but you're more intelligent. Downside is it still requires recovery and re-execution on misprediction. And it's also more complex, right? You have to have this predictor. So why are loads and store communication predictable? I'll just give you one example. So let's say you're doing a function call, right? If you do a call to a function, and let's say you execute some code and you do return, there are stores that set up the stack, right? For example, you want to pass arguments, you may want to store. Or you need some registers here. You spill the registers before you do the function call into memory, store them into the stack. And before you actually return from the function call, maybe you either do the loads here or loads here. Basically, you save the state onto stack, and you restore the state from the stack. Right. Now, these are relatively predictable, right? And their addresses may be computed differently. OK. OK. Any questions? This is fun, right? I'm not going to go into a prediction mechanism, but actually, I'll give you one prediction mechanism. So alpha 21264, remember the paper that I recommended? What it does is, when it first executes a load, if it has no information, and I'll tell you what that information is, it assumes the load is independent of a previous store. And it has logic that checks whether this is true, right? If it's true, there's no problem. If it's not true, the machine sets a bit in the instruction cache saying, oh, this load previously was found to be dependent on a previous store. So execute it conservatively, meaning wait until all previous stores' addresses become available before you actually schedule this load into the data cache. Or, yeah. Does that make sense? So it learns, basically. It's a very simple predictor, right? Initially, you're aggressive, but if you find the load to be causing this mispredictions, start becoming conservative. And it turns out this actually gets a lot of the benefit of memory dependence prediction. There are more sophisticated predictors, and these are actually two good papers if you're interested in this: dynamic speculation and synchronization of data dependencies, and memory dependence prediction using store sets. And actually, similar mechanisms are implemented in Intel and many of the out-of-order processors today. So what is the effect of this? Why am I harping on this a little bit? Because this has actually an important effect on performance. You don't want to serialize these instructions. That's pretty bad. This is a graph from that Christos and Emmer paper that basically proposed a memory dependence predictor that tries to identify which store a load is dependent on. And if you look at this, there are three graphs here, 3 bars here for each benchmark. And I believe these are spec 92 benchmarks. And y-axis is the instruction per cycle performance on an alpha, I believe it's an alpha 21364 like machine, which is the next generation of 21264, which never saw the day of light. But this is simulation results. No speculation means this is a conservative approach. You wait until all the store addresses become available before you schedule the load. Low performance. Naive speculation means very aggressive. You don't wait. Assume that the load is independent of any previous stores with a store with an unknown address. Performance, it's a little bit better, right? If you look at it, look at the middle bar, it's usually better than the white bar. So this tells you that most of the loads are actually independent of the stores. It's a better approach to do the naive speculation. But if you look at perfect, there's a big difference between the perfect. Perfect means you know exactly whether or not a load is dependent on a store. And if you, based on that information, you do the right thing in scheduling. And this is actually a beauty of simulation in C. You can design a simulator of a machine, and you can do these perfect studies. That's one of the benefits. You're going to do some C simulation later on in the course. And many companies, when they design processors, do this kind of simulation to understand the bounds. Basically, in a simulator, you can tell what is the right thing to do. For example, you can simulate a machine with perfect branch prediction, right? Because you can have a functional simulator like what you built earlier that functionally models what should happen in the program, and you can feed that to a performance simulator that actually simulates the performance of a pipeline, as you will do in one of your assignments later on. And you can always feed perfect predictions from the functional simulator to the performance simulator. So functional simulator, what do I mean by functional simulator? this is actually an ISA simulator, like what you built in the first lab, right? This basically tells you what should happen if I execute this program and if I obey the ISA. And you'd better obey the ISA when you execute this program. And you can feed from here into a performance simulator, performance model, or simulator, that basically models what goes on in the pipeline. Instruction fetch, I guess decode, rename, reservation stations, ... in C, retirement, ... But you can do some processing here and feed the instructions into the simulator such that you get the correct instruction stream, right? Because you determine the branches in this functional simulator. And you can feed an instruction stream with a correct branch prediction all the time, right? Similarly, that's what they did here. When they were simulating this performance model, it's simulating an out-of-order processor. When a load generates its address as simulated in the simulator, now they know because of this functional simulator, because there's something else happening, this functional simulator is also executing, perhaps part of the same thread, perhaps a different thread. They can tell if this load is actually dependent or independent of any other store in the machine. Right? And based on this, they can change the scheduling decision or make a scheduling decision in the performance simulator that is perfect. Right? So that's the idea. That's the beauty of doing simulation like this at the high level. That way you can see your performance bounds. How close are you to a perfect memory dependence predictor? And if you look at this, these naive mechanisms are not that close, right? They're actually applications that here, for example, this is a Perl. I don't know what prim means, but this is one way of using Perl. IPC is about 2 with these naive mechanisms. But if you can perfectly predict the dependencies of loads and stores and do the scheduling accordingly, IPC is almost 5. That's 2.5x performance just by scheduling the loads and stores correctly. Yes?
So it is superscalar?
Yeah, this is superscalar. That's right, IPC. This is actually an 8-byte machine. And the instruction window, I believe the simulation have an instruction window that's greater than 100 entries at least, maybe 256 entries. So of course, this problem becomes even more important if you have a bigger instruction window, right? Okay, so basically the takeaway is, well, this kind of simulation is important. That's one takeaway. That was a side for you. And the other takeaway is this problem is important. And it turns out simple predictors based on past history can achieve most of this potential. So this predictor in alpha 21-264 is not too bad. It gets close. But these predictors, which I'm not going to go into, that link stores and loads directly, achieve most of that performance potential. Okay.
Another question.
Yes?
How long does it take to warm up, though?
Warm up the predictors? Yeah, that's always an issue with predictors. It depends on how much state you have in the predictor. For example, the alpha 21-264 predictor, it warms up after one incorrect execution. But then it's hard to go back, right? What if that load is sometimes dependent, sometimes independent? So that's the downside of this predictor. Once it sees that the load caused a misspeculation, it always does the conservative thing. So it's very quick to warm up, but some of these others need to see the load multiple times to warm up. Okay, I think I'll leave you with one last thing. The complexity of this logic actually is one of the biggest limiters to scalability of an out-of-order engine. Let's say you want to build an instruction window with 4,000 entries. This becomes huge, right? Just to give you an idea, in Pentium 4, which had 126 entry instruction window, the size of this, I believe, was 24. So it had a 24 entry store buffer. 4,000 entries, again, let's scale it, because stores are perhaps 1/5 of the instructions, right? It's a good ballpark. So they followed a nice design, perhaps. 1/5 of the instructions, now you have 800 entries in your store buffer. Think about a CAM of 800 entries. And something else I did not tell you, actually, this is again food for thought for you, what if you have multiple stores supplying data for a single load? Why would this happen? Well, load is loading from 4 bytes. 1, 2, 3, 4. Each byte can be coming from a different store. Right? So it turns out it's difficult to do that directly. So many processors have an exception case in that case, if there are multiple stores supplying data for the load. That happens after all of those stores are committed. So if you write code that way and it doesn't perform very well, now you may know what might be going on underneath. OK. So there actually, this was a case study on some design choices that you have in an out-of-order processor, and a very important one. But there are many, many design choices when you design an out-of-order execution processor. One example that I'm not going to cover in any detail is, should reservation stations be centralized or distributed? The examples that we've seen in class, I guess I will cover it in a little bit detail. You have this, I guess this doesn't look like an adder. Adder, multiplier. And we had different reservation stations, right? Reservation stations for multiply and reservation stations for add. But this may not be the only choice. Maybe you want this, right? A centralized reservation station for both of them. Right? Guess what's the advantage of this versus this? Any guesses? Yes?
You automatically, when you have more than one, you automatically know which functional unit to dispatch the instructions.
That's right, exactly. So it's perhaps the selection logic is simpler here. Or put another way, here you can specialize the reservation station somehow to the characteristics of your functional unit also. And you don't need to search a bigger reservation station, perhaps. What else? It's also a general centralized versus distributed question. By the way, this is a really good interview question. If I was interviewing someone, I would ask this. Any other thing? Like utilization of these reservation stations? Which one is likely to be better? Here you're statically partitioning the reservation stations across different functional units, right? Whereas here, any reservation, any functional unit can use any number of entries here. Which means that your utilization is probably much better here because you have dynamic partitioning of instructions, or dynamic partitioning of reservation station entries across functional units. Which means that, for example, here, let's say you have 4 entries and 4 entries. What if you get 8 multiplies in your program? You need to stall here. If you had 8 entries here, you could accommodate accommodate those 8 multiplies, right? And they could execute. So you get better utilization, and you're less at the mercy of the characteristics of the code. Which means, basically, you can accommodate different instruction mixes a lot better with this approach. That's the upside. You can much better utilize these reservation stations, and probably you can get better performance because of that. Whereas here, some of the reservation stations can be empty, while you may need more entries in this reservation station. We'll see that this is, you can think of this as private reservation stations for each functional unit, or shared reservation stations across functional units, right? So anytime you have this private versus shared distinction, you have this issue of dynamic versus static partitioning. So what is the downside of this? There must be a downside, right? Any idea? No? You guys are waking up still?
You have to have a bigger single content addressable memory than that.
Exactly, right? It's more complex, basically. what you said was bigger single content addressable memory, which means you need to have a bigger search across this, which probably takes much longer. And also, your selection logic and wake-up logic becomes more complicated also, because now you're selecting across a bigger set of instructions. Whereas here, you're selecting across a smaller set. Make sense? So it's going to be more complicated, yes?
So I have a question. If there's just one reservation box, then would it be easier for the data coming out to be driving whatever it is?
I see. Basically, the value broadcast, you're saying. Yeah, you have, in a sense, it's kind of simpler, right? Because you always go to the same place, and routing may be a little bit harder here. But that also depends on the layout, where you lay out these things.
So that's dependent.
Yeah. You still need the same number of buses, right? Yeah, because you need one coming out of here and one coming out of here, or a common data bus going to all of them. But here, everything goes to the same place. But exact layout, that really depends on where things are laid out. Okay? Okay, there are other advances and disadvantages, but I'll let you figure that out. So one other, actually, you can think of the load here also, right? Load units. And it has reservation stations also. One other thing is you can customize these reservation stations once they're private to the functional units. Whereas here, each reservation station entry should be general purpose across these functional units. For example, you may not need the address and data for here, but you will still need to have it because it's a general purpose reservation station entry. So many processors today use this approach because it's easier to design in general, and you don't want a monolithic reservation station becomes more complex, as you said. Okay. Another question. Should reservation stations and reorder buffers store data values, or should there be a centralized physical register file where all data values are stored? Remember, in the example we showed, we had the data values in the reservation stations, right? Basically, when an instruction reads a register, it copies the value from the register file into the reservation station, assuming the value is available. If the value is not available, you're wasting space. There's some data over there, right? What if all of the instructions are reading register 2? Yes?
Well, I was going to say that because we only care about data or tag, because then we can at least use that same register, that same space for either the data or the tag, depending on the bit. So we do save some space because we do need to at least save the tag. But of course, if the data is like 32 bits and the tag is only 5 bits,
that's right. No, that's clever actually. You're right. You don't need to have separate storage for tag and data. You can utilize the same space for both because you don't need both at the same time. Absolutely. That does reduce the space a little bit, but that doesn't solve the problem I'm just right now going to describe. What if all instructions are reading register 2 and register 2 is available? Then all instructions copy register 2 to their reservation station entries. It sounds like a waste, right? So many processors today, what they do is they only have pointers to registers, which means that when they access the register file initially, the register file doesn't even contain the data. The register file basically associates a tag, which is the physical register file entry. So you have this future register file initially. Remember what we had was, I guess this is too small right now. We don't want that. Before, what we had was val-bit tag data. Instead, what we will have is, I guess, a tag. And you can have a val-bit too. But basically, what we'll have is a physical register file entry for this future register. So if register 0 is at physical register 5, register 10 is at physical register 16. Or register 10 is going to come from the instruction that's going to produce physical register 16. This way you basically have a pointer, right? You don't have data. And when you get this, when you rename an instruction, you don't read the data. When the reservation stations, you basically have this tag. Actually, you do have the valid bits here. What you do is you take the valid bit or ready bit and the tag, which is essentially the physical register ID. And when an instruction produces physical register 16, let's say physical register 16 was not valid, and this instruction that you just renamed requires physical register 16, it has the tag physical register 16. When the instruction that produces physical register 16 executes, it broadcasts that tag physical register 16. This is just a tag, not the data. Data is not broadcast anymore. And this becomes now ready. The instruction that produces that tag, produces physical register 16, at the same time writes its value to this physical register file, 16. And data is there, basically, some data, 10, let's say. When this instruction becomes ready, it knows where to get the data. It has the pointer to physical register 16. So it accesses this other file, physical register file, that contains the data. Make sense? So this way, you don't need to duplicate the data across everywhere. Now you got rid of the data from the register file. There are reservation stations. You got rid of the data entries from the reservation stations. You got rid of the data entries from the architectural register file too, right? Now what do I mean by that? What I mean is architectural register file. Remember, architectural register file is updated when instructions are committed. It's at the back end of the machine. It doesn't need to contain data anymore. All it needs to contain is when this instruction that's writing to physical register 16, let's say it's actually producing register 2. When that instruction retires, commits, it says, oh, I'm committing register 2, but I've already written the value into the physical register file. So the new value of new architectural value of register 2 actually resides in physical register 16. That's my architectural state. I have a pointer to the data. Right. And now I can, basically this physical register file contains all of the registers in the machine, including the architectural registers. And architectural registers are essentially, you can figure out what are the architectural registers by looking at your architectural register file. It's not an architectural register file anymore. It's basically pointers to the architectural registers or architectural register alias table. You can call it that way. Right. It's really pointers. That way you can get rid of a lot of the inefficiency that we've discussed. And many existing machines actually do this. You can read the papers that I described. Pentium 4 does this. Pentium Pro did store the registers in it did store the data in the reservation stations. So it was a little bit less efficient. But now the Intel designs that are based on Pentium Pro don't do that anymore. OK. Anyway, I think I've covered a lot of these details, but there's a lot of interesting design choices you have. And I think I've answered this question earlier. Exactly when does an instruction broadcast this tag? It doesn't broadcast it when it actually produces the value. It broadcasts it earlier, right? So that you can schedule the dependent instructions such that they can get the value from the forwarding paths. And there are many more. Some more food for thought for you. I'm not going to cover these in detail. But how can you implement branch prediction in an out-of-order execution machine? I'll let you think about this. There are issues related to this. Because branches can execute and resolve out of order, right? So do you update the pattern history table when a branch is resolved? Or do you update the pattern history table when a branch is committed? Well, it could take a while for the branch to be committed, right? If you have a 128 entry instruction window, your updates may be delayed. And what if you fetch the next iteration for that branch? Then you don't have the information from the last few executions, right? When do you update the branch history register? Is a question also, right? Do you update it speculatively, meaning when you fetch the branch, or do you update, no, do you update, remember the branch history register contains which direction earlier branches went, right? If your instruction window is 128 entries, well, you may not know which direction earlier branches went, right? Because they are executing out of order. But you need this information when you fetch the next branch, right, to be accurate. So do you update the history register speculatively with the predictions that you made? Or do you wait until commit time? So there are a lot of interesting issues related to this. And it turns out you do need to update it speculatively. Otherwise, you have incomplete information to do the branch prediction. I guess this is one of the reasons why we don't design the entire out-of-order processor with branch prediction in detail in this course. But how can you combine superscalar execution with out-of-order execution? I'd encourage you to think about these issues. So I guess, first of all, superscalar execution is very different from out-of-order execution. These are totally different and orthogonal concepts. Right? Out-of-order execution, it's basically executing instructions out of order. It says nothing about how many instructions you fetch or execute concurrently. You can have multiple functional units and have out-of-order execution. But you can only fetch one instruction per cycle. Superscalar execution, fetch more than one instruction per cycle. Completely orthogonal. The problem is when people refer to superscalar processors, they also imply out-of-order execution. But keep these concepts separate in your head. So what are the issues? When you're fetching multiple instructions per cycle, you need to rename multiple instructions per cycle, right? Now think about what that logic looks like. You basically need to do the renaming, and instructions may be dependent on each other serially, right? If you have 4 instructions that are fetched and they're all dependent on each other, you'd better get the renaming right. Add R1, R2, maybe R2 something, R3, ... right? You'd better assign the names correctly here. So this is a dependent renaming logic. Make sense? And this complicates, actually. As your width increases, this renaming becomes more complicated, too. And, of course, you need to broadcast the tags concurrently if you want to make full use of a superscalar engine, right? If you want to retire 4 instructions per cycle, you'd better have 4 broadcast buses at least. Right? You cannot have a common data bus, basically, which means that the logic becomes more complex, too. You have a lot more comparators. OK. And then how can you combine superscalar execution, out-of-order execution, and branch prediction, which is what existing processors are? So there are a lot of interesting issues there. And I will not talk about that, but if you're really interested in this, these are some very good references that describe some of these processors. The Alpha 21264, I would definitely recommend that. This describes the microarchitecture of the Pentium 4. And this describes the MIPS R10000, which is not a microprocessor without interlocking pipeline stages, as we discussed last time. Actually, I would probably add to this the IBM Power 4 microarchitecture, which is a nice paper also. It's by Tendler and others. It's called IBM Power 4 microarchitecture, and we should probably update the slide. It's an IBM Journal of Research and Development. And it is an out-of-order machine also. It's actually a beautiful paper. It describes a lot of the issues we talked about. OK. Any questions? Now you're all excited about building an out-of-order machine? No? Maybe not. It's fun, though. OK. So I think what I'll do is let's take a break for 5 minutes, and then we'll start covering some other execution models, the alternative ways. IBM actually has very nice papers in their Journal of Research and Development that describes Power 4, Power 5, Power 6. I don't know if there is one for Power 7 yet. There is one? OK, good. And also the Z series now, I think. Those are very instructive papers in terms of their designs of these aggressive processors. And they're detailed, too. And you can access this Journal of Research and Development through IEEE Explorer, through the CMU library. No, we didn't have access, but we finally have access to it. It used to be free from the IPM site, but somehow they went through this way. I wish they go back to free, hopefully, at some point. Okay, so let's talk about other approaches to concurrency. Certainly, superscalar out-of-order execution, superscalar and out-of-order execution is not the only approach. In fact, you've seen others. I'm going to cover one of them very quickly, Dataflow machines, which has not been successful, Dataflow at the ISA level. But I think it's instructive to look at things, like why hasn't it been successful. These are some of the approaches to instruction-level concurrency, basically. How do you figure out dependencies between independent instructions and execute them concurrently somehow? Out-of-order execution is one. Dataflow at the ISA level is another one. We'll talk a lot about SIMD processing, single instruction, multiple data, and very long instruction word, which you're familiar with by now a little bit. We're going to cover that a little bit more. There are other approaches, systolic arrays. We'll talk about that briefly. Basically, you pump the data into a bunch of functional units or maybe processors, and those processors transform the data into something else and move it to or pass it on to some other functional units or processors, and they transform the data to something else and pass it to the next set of functional units. And then, eventually, the last set of functional units write the data to memory. It's like a systolic architecture. Heart pumping blood into your system, and these things, it flows through the veins, go to the cells. Cells do some processing on the blood, and eventually, the blood, the data out, comes back into your heart, right? And then you get some more data, and you keep pumping data in and out. This is actually a nice concept. Maybe we will cover this a little bit, but if we do not get to it, since we don't have enough lectures in this term, right? If you're interested in this, this was actually developed at Carnegie Mellon by H.T. Kung in the late 70s, 1970s, early 1980s. And it did influence specialized architectures significantly. And if you're interested in this, Kung has a very nice paper called Why Systolic Architectures. I think it's IEEE Computer 1982, right? And Justin or Jason can correct me if that's wrong. I got the title of that other paper wrong. Okay, but basically the idea is simple. You can have a simple functional unit here. I'll call it functional unit 1. And you have, I guess let's call it memory. You pump the data, and this functional unit does something on it, passes on to the next functional unit. And this functional unit actually can be complicated. It can be executing a program. It can have its own memory. Passed on to the next functional unit, which does something to the data, outputs, passes on to the next functional unit, which does something, ... Last functional unit puts it back to memory. This is your heart, right? And this is the blood that's being pumped and flowing through your veins and going back to your memory to get cleansed. That's the idea. Why this is good? Because now, with a given amount of data, you can do lots of processing. You don't need to go to memory every time. Load, store, load, store, load, store. You don't need to do that. You basically send the data, and processing happens here. And there's a very nice example in this paper that describes how you can do convolution or filtering with this. You basically send the data in, and each functional unit does some operation, part of the convolution operation, like x1, y1, for example, x1, y2, on two inputs, right? I won't go into convolution here, but I assume that you guys have taken courses where you learned about convolution. If not, this is a good description of that also. But that's the basic idea. And now you can actually do image processing operations, right? You could progressively change the image. And this was actually used in many image processors. You don't have a single linear array of this, but you can have a two-dimensional array of functional units like this. I guess I'll do it here. You can have a grid of these functional units. And what you can now do is send an image here. Maybe the pixels of the image keep going in. Think about this as a 1024 by 1024 grid. Maybe each pixel is being operated on by a different functional unit. And you pump it in. And maybe you pump in some other data from the top. Maybe you compare two images. I don't know. I'm just making it up. Maybe you add two images together. As we will see later on in SIMD operations, maybe you take some pixels from one image, and if it matches some value, you pick this image's pixel. If it doesn't match that value, you pick this image's pixel. This is when you're putting together two images, right? And we will see an example of this in the Intel MMX architecture, how to do that. But this is a very natural fit for that, right? You're basically pumping in data from multiple ways. And you can actually have little programs executing on each. And this way, you don't need to go through memory. You have these specialized interconnections between these processors that basically move the data very, very quickly. No need to go to memory every single time for each processor. It's specialized. And this was very good for image tasks and vision tasks. Those kinds of processing where you have lots of data and you need to operate on, you can operate them, on them in parallel. And Kung, actually, H.C. Kung built the warp computer that was used for these tasks. And you can read that paper, which was the initial paper. But there's also another paper, I believe it was by Anna Taron, or I cannot remember the name very well, but it's basically called the warp computer, architecture and implementation. I'm not going to talk about that. Write it. ISCA 1986, that describes the experiences with such an engine. It's quite interesting. So think about many different ways of processing data. Right? It's not, data flow is different. This is very different from data flow also. It has some data flow concepts though, right? You're feeding things, but it's not that general purpose. Right? Somehow, your program needs to look like this. But you can make it general purpose if this is perfectly programmable or fully programmable. So if you have some program running over this functional unit, which is now a processor, processor 1, processor 2, processor 3, now it's becoming much more programmable, right? And maybe you even have some local memories here. So this actually led to what is called stream processing. If you think about this, it's essentially stream processing. You send a stream in, and a program operates on the stream, generates a stream out. Another program operates on the stream, generates another stream out, ... And eventually you have an output to the user. OK. I guess I did talk about systolic arrays in a nutshell. And decoupled access execute is another paradigm, which I will again briefly describe. The idea is you want to get some of the benefits of out-of-order execution without the cost. And you saw the cost, right? The cost could be very high, especially if you need to broadcast all of those tags all over the place and do the comparisons between stores and loads. Here the idea is, can we get that benefit simply? And basically, you have an access processor where you do the loads and stores, an execute processor where you do all the other operations. And your program, when you fetch the program, you basically decide whether an operation goes here or here. And now you can have some parallelism between access and execute, right? It's not in order. While you're doing loads here, load, you can do independent add, multiply, ... And each of these can be in order. Right? And then you, of course, need to somehow do reordering at the end. That complexity doesn't go away. But now what you're doing is, while a load is being stalled here, if there are independent execute operations, ALU operations in the machine, you can execute them, right? You can tolerate load latency this way. Okay, so how do you communicate between these two? Actually, when this was proposed, you can communicate via queues. Basically, a load, when it generates its value, puts it into a queue, and an execute operation gets it out of the queue. And these are specified in the ISA. Similarly, you have a queue from the execute to access, because if some operations can be generating the address for the load, right? But because load latency is high, to tolerate load latency, you can have a lot of independent operations here. That's the idea. You can tolerate the long load latency by executing independent operations in the execute processor. And this was actually also implemented in some specialized engines. There used to be a company, I think they still exist, Astronautics. I think this was implemented in the Astronautics DS1 processor. Jim Smith, whose papers you read, or you've been seeing, was the person who developed the idea. And again, you can read another paper if you're really interested in this. I believe it was called Decoupled Access Execute Architectures. I'll call it DAE architectures. And the Astronautics DS1 processor. This is a later paper, but originally the idea is take this. It was an ISCA 1982, and Justin can put this online also if you're interested in this. But this is a different execution model also, right? Okay, so limited out-of-order execution by changing the ISA a little bit. Okay, now let's take a look at some of the other ones. Dataflow. Now, you know what Dataflow is, so I'm going to go through this relatively fast. I'll just show you some example machines. Dataflow is good at exploiting irregular parallelism, right? You've seen this by now. If you have a complicated Dataflow graph, you can figure out what is independent. And that's what an out-of-order machine does. And I'll flash these. Basically, we had this Dataflow graph here, right? And this could be a good homework question or an exam question. So you should be able to draw the Dataflow graph by just looking at this. It's not that hard. We did it last time, right? Dataflow at the ISA level is different, right? Here, the out-of-order execution machine draws the Dataflow graph. At the ISA level, the ISA specifies the Dataflow graph. That's the big difference. And here, how is the Dataflow graph specified? This way, basically. You basically have a destination of where the results should go and where the results should actually not come from, but what are the arguments coming in. And you've seen the Dataflow graph, so I'm going to just flash through these. This is a more detailed slide. This is from Arvind at MIT, who worked a lot on Dataflow machines. They actually implemented Dataflow machines. Dataflow machines were very popular in the 1980s, but they never took off as a general purpose processing paradigm. But basically, you have tokens as part of these Dataflow graph arcs. Basically, values are tokens which specify which instruction should get that value, which port of that instruction should get that value, left or right operand, and what is the data value. And when this instruction fires, executes, it basically generates a token in the machine, which is a packet, that contains all of this information. This value should go and find the instruction at this instruction pointer, which is 3, and it should go to the left port of that instruction. It should check if that left, it should basically enable that left operand. And this is the value. This is very much like out-of-order execution, right? You're doing a tag broadcast here. What is a tag? Well, I guess in this case, the tag is really the instruction pointer. And also the port, which value, which operand, and the data value. Except the ISA explicitly tells you this. When you produce this value, when this instruction produces its value, it should go and wake up this instruction at instruction pointer and this port. Well, not wake up, but it should enable, it should make ready the port, this port of this instruction at this instruction pointer. Okay? Well, I guess I've given you that. No separate control flow, as you've seen before. And you all know what this does by heart now, right? You remember? Factorial. Good. Good. And this is just for your study, basically. I like this illustration from a paper earlier that I think it's a paper by Trelevan that compares data flow architectures, 1982. But basically, this is a nice illustration of what data flow machine looks like. This is control flow machine. You basically have data memory, and instructions reference data memory, and instructions communicate data from that memory. And you can think of expanding this into registers also. But you have this implicit control flow that happens between instructions. Whereas in data flow, you basically have pointers. When an instruction produces values, it basically enables other instructions to execute, get those values. So you can think of memory as value communication here. Whereas here, you have storage locations for memory. Okay? Okay, what are the characteristics of this? It's basically data-driven execution, right? You can think of this as instruction-level graphical code. It's data flow graphs. Nodes are operators, arts are data, and this is as opposed to control-driven execution. The key thing is only real dependencies constrain processing, right? And there's no program counter. Operations execute asynchronously. You can build a data flow graph for your entire program this way. And execution is triggered by the presence of data. And you knew all of that. So people have actually built these processors. A generic-looking processor looks like this. This is basically your pipeline. Let's start with the data flow processing element. Data flow processing element basically receives some execution packet, let's call it. It gets data 1, source value 1, source value 2. It gets the opcode. It gets some tag. Ignore this tag for now, but basically it tags the value. And it also figures out what is the destination of this result. And it does the operation. It has the operation, and it does the operation on the data. And it generates a token. And token is, remember what the token was, right? It's the tag and the destination. It contains the instruction pointer. It contains the port. It also contains the data value. And this is fed to this matching area. Now, what is this matching area? This is where the instructions are waiting, or unmatched tokens are waiting. Basically, here, what happens is there another token waiting for the same instruction for a different port? So you have two. Where is this thing? I guess our load store queue is gone now. So hopefully you've taken pictures. But you can find it online too, right? Okay. So what does that matching store look like? Basically, that matching store looks like if there could be an entry that says this IP is waiting, or let's call it a tag, or this destination. Don't worry about the different tag over there now. This is waiting. This already has its left input, and this is the data value. Right. When a token is produced, it generates a location. It generates an entry like that in the matching store. Now, another token comes. Let's say this is getting to IP 0. Let's say this IP 0. And I guess you can have left or right, ready or not ready. And this is the data value for the left, and this is the data value for the right operand. When, let's say, the left value is already produced, it's waiting in this matching store. When another token is produced, it basically checks if the corresponding source value is already available, right? So let's say what we're getting is IP0, right source operand. Remember the ISA specified which source operand this token corresponds to, and the data value. in this case, data write. What happens in this matching store is what we've seen in an out-of-order machine. You compare IP, R, you have a big CAM that looks at, well, I guess you don't do the R, but you check if this IP matches this other IP, any of the IPs here, or tags here. And if there's a match, then in this case, it's the right operand. Right operand is ready, and left operand was already here. Now this IP can execute and can be fetched. Make sense? The instruction at that IP, instruction pointer. I'll give you a very quick overview of it. But that's essentially tag matching, similar to out-of-order execution. You generate some tag, and you fetch the you figure out whether an instruction, whether there's a value that's produced for the same tag, for the same instruction. If there is, that means that both operands are ready. If there isn't, then you store the value here and wait for the next operand to become ready. Right. And when the tag matches, which means that the instruction is actually ready, then the machine goes and fetches the instruction from memory, and then forms this execution packet. Now it says data 1, data 2. So if you look here, the token is data 1 plus tag and destination. Using this, from the pool of unmatched tokens, we fetch data 2. And we get data 1, data 2, and then also a tag and destination coming from the instruction. And we fetch the instruction, and the instruction specifies the new destination, right? Where should the result go? That's basically what's happening here is you have this. When we broadcast, if you look at the graphical version of this, what happened here is somebody already generated this token. This token or value is waiting here. And when this instruction executes, it broadcasts its own token. And in this matching store, you check whether this broadcast token actually has a corresponding token, which means that they need to have the same tag. And if they do, then the instruction fetch area, that logic there, fetches this instruction and forms a packet to be executed in the data flow processing element. And this instruction also has a destination, right? And a token, and a new token is generated for that destination, right? That's the idea. You have this loop, basically. And this logic is complex, right? Basically, this is a big tag match. If you think of a big data flow graph, you may, at any point in time, have lots of tokens that are not matched yet, right? So you may be storing this token, maybe storing, I don't know, I don't do a good job generating data flow graphs, I guess. That's the lesson here. But many of these tokens may be waiting for their corresponding tokens. Many of these instructions basically may be waiting one of their source operands, which means that you need to have this matching area big. And since data flow has really no control over the size of the program, in a control flow machine, you're basically going through instruction by instruction. You know where you are. In a data flow machine, there's really, the program can be as big as you want it to be. Right? So you may have actually millions of these nodes. And this was a problem in data flow machines early data flow machines. How do you control the size of this matching area? It's not only that this is complex, but controlling the size is a problem. Well, in hardware, you have some limited size, but what if you overflow that? Because there's no guarantee. In an out-of-order machine, there's a guarantee, right? You don't put an instruction into the machine before you know that you generate, well, basically, you don't put an instruction in the machine out of order, right? Whereas here, everything is out of order. You may have lots of tokens here waiting. OK. So this was the, this is a generic data flow processor. I'll give you two examples of this. This is the MIT tag token data flow architecture. Basically, we have this token queue. Again, if you look at this execution unit, it forms tokens. And this is the memory interaction. Let's ignore that for now. Basically puts the tokens in a queue. And then the tokens go into this wait match unit, which tries to match incoming token and a waiting token with the same instruction address. If there's success, both tokens are forwarded, instructions fetched from program memory, and the instruction is executed. If there is a fail, the incoming token is placed into the waiting token memory. And the instruction is not forwarded in that case. So you have a bubble. And I think I'll leave the examination of this for you. But basically, what I described in pictorial terms are in those slides. Yes?
Is the ISA still a new machine though?
No, not at all. The ISA is still, the ISA basically is this. The ISA looks like this. This is an instruction, actually. If you look at the program memory, this is location 109. This is the opcode, and this is the destination of the result, where the result should go. It should go to 120, left port. Right?
Wouldn't that be overly complicated for a programmer to use?
That's right, yes. Exactly. How do you generate code for something like this? In a sequential machine, everything is easy to reason about, right?
So you need like a translation layer that's probably more powerful than your normal compiler.
That's right.
That breaks down what the user wants to do into the token tag system.
That's right, exactly. And that was part of the problem, actually. This, while these machines were beautifully designed, the software stack on top of them were not designed. And that's one of the reasons why these were not successful. Actually, if you listen to Arvind's, well, you cannot listen to it anymore, but Arvind gave a nice keynote talk at the International Symposium on Computer Architecture in 2005. And he identified that was the big reason why these machines were not successful. He said we should have done a lot of research into software. If you were doing it all over again, we should have actually investigated how to build a software stack for these machines. And that gives you the importance of the software stack, right? In the end, it's really the programmer. If you cannot program these machines efficiently, it's very difficult to design. However beautiful your architecture may be, it's very difficult to get that adopted in practice. So never lose that big picture in mind. This is great, I think. This is great for research and understanding. And it did lead to a lot of the out-of-order execution concepts, as you can see, right? Okay. But I think this gives you an example. Basically, this is your program in memory. It basically is a data flow graph. Every instruction explicitly specifies its destinations. And you can ignore some of the things that you do not necessarily understand here. And this gives you an execution of an instruction. But I'll not go into this in detail. And you can see that this is a data flow example with memory. You'll be able to understand it when you look at it. Okay. There were actually many data flow machines at this time. This was the University of Manchester data flow machine. And there are a bunch of data flow machines from Japan. And many of them were used for purposes, different purposes, specialized purposes. But if you look at this, it's very similar. You have a token queue, you have a matching store, and a node store. Basically, this is where your instructions are, and a processing element. And the machine looks like this, keeps operating. And here you see an overflow unit. Right? Now, what happens here is if you have a large data set, large program with lots of tokens, this matching store overflows. Well, you want to build this small so that you can keep executing very fast. If you make this large, it's essentially your, I don't want to call it the instruction window, but this is where you check the readiness of an instruction, right? If you make it too large now, you have the big CAM, content addressable memory. But in this case, there is no control of parallelism, so you're overflowing this matching store because there are new tokens coming in from some other part of the program. In fact, think of your entire system as data flow, right? Your entire system needs to be a data flow machine, like your operating system. How does the operating system interact with your program? When you get an interrupt, what is it? It's really you connect to another data flow graph, basically, somehow. So it's really, your entire system needs to somehow fit. It's not only your program. Okay, so what are the advantages and disadvantages? This is a fascinating topic to think about also, I think. The advantage is irregular parallelism. This is maybe the best known way of exploiting irregular parallelism. Because only real dependencies constrain processing. Disadvantages, there are many. And you know this. No precise state, which means that these are very difficult for the programmer to reason about. debugging is very difficult, and you know why, what the reason is. Bookkeeping overhead is high, tag matching, that tag store, there's a reason why you have overflow units. There was too much parallelism. Parallelism control was needed in these machines, and these machines explicitly, programmers modify the data flow graph such that you don't have more than n number of iterations of a loop, for example, in the machine. There were explicit modifications to the data flow graph to do that. Because if you had more, then you would overflow these tag matching units. And I'm not going to go into this in detail, but think about how to implement dynamic data structures on this, like a linked list. How are you going to do that? It's not that easy, actually, but I'll let you think about it. I'm not going to test you on it either. But it's a good exercise. And in fact, people have spent a lot of time to try to figure out how to implement this. You still need memory, so it's not as beautiful anymore. You still need some persistent memory somewhere. But now you need to have the data flow graphs to operate on it. Yes?
Well, so it's pretty much taking advantage of irregular parallelism. But isn't the hardest part really to discover those irregular parallelism, not to take advantage?
Well, in a sense, it provides you a mechanism to discover it, right?
Right.
Which is your programs actually give you what are the dependencies, and your machine discovers it based on those dependencies.
But then still a user-driven exercise.
That's right. Yeah, someone needs to provide those dependencies. Absolutely. Yeah.
Another question is really if the program itself doesn't. So if the user doesn't specify any type of parallelism, how can the machine discover those parallelisms?
Yeah, you cannot. Yeah, I mean that the ISA needs to specify the dependencies. There's no question about that. That's data flow. Out-of-order execution discovers those dependencies, right, underneath. And that's the difference. So out-of-order execution has been successful because it didn't put the burden on the software stack. Okay, actually, yeah, that's the next slide. To summarize, you already know what this is, basically. Availability of data determines order of execution, and programs are represented as data flow graphs, and somebody needs to produce that. And data flow at the ISA level has not been successful at the general purpose market, which is a big market, because of these disadvantages. And perhaps the first one is the biggest one. But data flow implementations under the hood, while preserving sequential ISA semantics, have been very successful, as we've covered in the last lecture, right? There was a big list of, well, I've given you some papers, including that thing that disappeared from there. And it's actually, basically that's out-of-order execution. And this is another paper you may want to look at if you're interested. And it's called, if you look at this, I think the reason I put it here is because it says a high-performance restricted data flow architecture having minimal functionality. So the complexity is low also if you have a restricted data flow engine. So if you want to do more reading, you can read about the Manchester Data Flow Computer. It's a nice paper. It's a little bit tough to understand, but it gives you the basics. And the microarchitecture level data flow, which you already know about at this point. OK, let's go into vector processing. There's no way we're going to finish vector processing, but this is another fascinating execution model, I think, which has been widely successful as opposed to data flow at the ISA level. This at the ISA level has been successful also. Let's start with a taxonomy of computers. This is Mike Flynn's taxonomy of computers in this paper. If you think about an instruction and a piece of data, you can categorize a computer based on whether or not it has a single, each of these as single or multiple. Single instruction, single data computer is a computer where a single instruction operates on a single data element. Kind of obvious, right? This is what we've seen, right? The MIPS ISA is like that, at least the instructions that you're implementing. Right? Single instruction, single data. Single data doesn't mean that you can still have multiple sources, right? Of course, you need to add those, but it's really a single logical data set. Whereas SIMD, now single instruction operates on multiple data elements. You do the same operation on multiple sets. And we'll see array processors and vector processors. And GPUs are an example of a combination of both. MISD is kind of weird. You have multiple instructions operating on single data elements. You could argue whatever I showed you here is kind of like MISD. Uh-oh, it disappeared. Okay. This is kind of like MISD, maybe. You supply one data element, and multiple instructions operate on it, and they transform it somehow. It's not perfect, but that's another category of processors. And there's also a MIMD, multiple instruction operate on multiple data concurrently. Basically, you have multiple instruction streams, and these are multiprocessors or multi-threaded processors. Now we're going to talk about SIMD. We've been looking at SISD a lot, and we're going to talk about MIMD later on in the course. So what enables SIMD is really data parallelism, where concurrency arises from performing the same operations on different pieces of data, or same operation on different pieces of data. For example, if you take a dot product of two vectors, you're basically doing the same operation on every single element, right? Contrast this with Dataflow. Here, concurrency arises from executing different operations in parallel, right? In a data-driven way. And contrast this with thread parallelism. Here, this is more like MIMD. Concurrency really arises from executing different threads of control in parallel. Here, we're going to do a single instruction on multiple data. SIMD also exploits instruction-level parallelism, because you're really exploiting parallelism between different operations, right? Except they happen to be the same. The instructions happen to be the same. They happen to be operating on the same data. And you're really executing them in parallel. Right? OK, what is this? What is SIMD processing? I already given you this, basically. Single instruction operates on multiple data elements, but you could have it in time and in space. You could specify the instruction, and the instruction can operate on multiple data elements in time or in space. Basically, you need to have multiple processing elements, obviously, to enable this. Let's take a look at this time-space duality. Existing GPUs, for example, have both time and space. A single instruction operates on multiple data elements in both time and space, and we'll see what that is. An array processor, the instruction operates on multiple data elements at the same time, which means that you'd better have the same functional unit, multiple copies of the same functional unit, right? A vector processor, these are very traditional definitions. Instruction operates on multiple data elements in consecutive time steps. The first data element, cycle 1, the second data element, cycle 2, third data element, cycle 3, ... And you can see this time-space duality. This is an array processor. You have these processing elements. They're all identical. Basically, you can do 4 of the same operation at the same time. Vector processor, you have these processing elements. They're not identical. Now you see the one difference quickly, right? This is probably less costly, assuming you want to do the same operations, and you do want to do it. And let's take a look at our instruction stream. This is a cooked-up vector program for you. We're going to see the vector instructions in much more detail soon. But basically, we want to do a load from this array into this, what I'll call the vector register. And the array has 4 elements. And then we're going to add 1 to each element in the array. That's what this means. Basically, what we're going to do is we're going to add, I guess if I decode what this program does, hopefully I should be able to do it. What that program does is it takes array A, and for each element in the array A, you add 1 to it, and then you multiply this by 2, and you store this value into array A again. Basically, that's what you're doing. Now, if we make this nicer, for I equals 0, I less than 4, I plus plus, what we're doing is AI equals 2 times AI plus 1. Nicely cooked up program. Somebody will do it. OK, so that's this program. How does it execute on an array processor? Well, basically, the first load is you're doing a load on all of the elements at the same time, right? Well, load of the first element, load of the second element, load of the third element, fourth element. They're all in parallel. Next cycle, adds. Add 1 to the result. Next cycle, multiply the result by 2. Next cycle, store the result into the array again. Done. Right? how does this work on a vector processor? And now you're exploiting a single instruction multiple data parallelism, right? Now think about this. You don't need to fetch 4 different loads here, right? You fetch one load, and that load operates on multiple data elements. Vector processor, the first load starts operating on the first element in the first cycle. In the next cycle, the same load operates on the next data element. At the same time, you start the add on the first data element. Next cycle, the second data element, or third data element for this load, the second element for add, first element for multiply, dot, dot, dot. Right? So if you look at the array processor, you're doing the same operation at the same time. If you look at a vector processor, you're doing different operations at the same time. Right? And if you look at space, in an array processor, you have different operations at the same space, whereas a vector processor, you're always doing the same operation at the same space. So you save space here. Right? Whereas here, you'd better be able to have the ability to do different operations in the same space. OK, so this is the fundamental distinction between these two. As I said, we're going to see today's processors doing both. OK, so what's the difference between this and VLIW? This is important. What VLIW does is the compiler packs independent instructions as a single long instruction word, right? Very long instruction word. You have the program counter, you fetch independent instructions. And these independent instructions can be totally different. Add, load, multiply, move, multiply. And they can be operating on totally different, unrelated data elements. And these instructions go into the functional units directly. And there's no dependency check logic because the compiler ensured that these are independent. Now, if we take this picture, a vector processor looks like this. An array processor looks like this. You have the program counter. You have one instruction, add, except it operates on a vector register that has a length 4, which means that it operates on 4 data elements concurrently. Now you fetch that, and this is what happens. Concurrently, you execute 4 operations that are all the same except on different data elements. This executes on the 0th, 1st, 2nd, and 3rd element. So VLIW, independent operations executed the same cycle and fetched. Here, array processor, you fetch only one operation, but execute on multiple data elements. Make sense? Which one is more flexible? Any guesses? VLIW or array processor? VLIW, right? It's more flexible because now you can execute multiple operations that have nothing to do with each other in the same cycle. Whereas here, well, you're restricted to actually executing the same operation across multiple data elements in the same cycle. If you cannot do that, for example, if you do not have a 4-element vector, if your vector has only one element, which means that you have a scalar value to operate on, well, you cannot utilize these functional units in the same cycle, right? OK. And we'll see how other processors, vector processors, solve that problem. They actually had scalar units. In fact, they had scalar units that are faster than any other scalar unit at their times. And we'll see why that's the case. You can start thinking about that. So what is a vector? A vector is really a one-dimensional array of numbers, right? You've all programmed with vectors probably. And many scientific commercial programs use vectors. And this is my cooked up example of, I guess, averaging to arrays in this case, or vectors. And a vector processor is one whose instructions operate on vectors rather than scalar, single data values. You operate on multiple data values. What does this take? Well, what are the basic requirements for this? First, you need to have the ability to load and store vectors. And we're going to do that with vector registers. So most vector processors today have vector registers that contain vectors. Not a single scalar value, but a vector value. It's a data type, right? Remember the ISA lecture we had earlier? Well, our data type is a vector. By the way, just as an aside, old vector processors did not even have registers. You could operate on vectors in memory, right? But many vector processors today have registers. And you need to operate on vectors of different lengths. So you need to have a register that specifies the length of the vector. You don't want to be rigid, right? If you have a vector of 32, you'd like to be able to specify that. And sometimes you have a vector of 2. And elements of a vector might be stored apart from each other in memory. Right? Again, you want some flexibility. You don't want to always, and we'll see why that's the case, why this is important. Actually, I'll just give you the basic idea, basic reason why this is the case. Let's say you have a matrix. And if you look at this matrix, you have rows and columns. And let's say your memory is, this is 0, 1, 2, 3, 4, 5. I guess this is the memory location. 6, 7, 8, 9, 10, 11. And 12, ... Let's say if you want to operate on this vector. If you look at this vector, consecutive elements of the vector are stored one location, one memory location apart from each other, right? Which means that your vector stride is equal to 1. Make sense? Stride is the distance between two elements of a vector. And we need this. Why? Because sometimes you want to operate on this row. In that case, your stride is 1. And when you're loading this data structure, this matrix from memory, you'd better load 0, 1, 2, 3, 4, 5. You specify a base address, which is 0, a stride, which is 1, and you specify a vector length, which in this case is 6. And what the machine does is, it does a load. Starts with the base address, loads that value, increments the base address with the stride, loads that value, increments that address with the stride, loads that value, until it does this operation vector length times. Make sense? This is nice if you're loading this part. What if you're loading a column? Well, now the consecutive elements of this vector are not in consecutive locations in memory. They're apart. There are 6 locations apart from each other. Right? So if you want to load this vector, what do you need to do? Base address is still 0. Stride is now 6. And vector length is, I guess I did not specify it, but let's say we have 20 elements here. Vector length is 20. Right? 20 rows here. Their vector length is 20. Now we're flexible, right? We can load pretty much anywhere from memory, as long as the elements are spaced equally from each other. So you see you need some regularity in this code, in the layout of the data. And that's exactly what GPUs require. They need regularity in the layout of their data to be able to do these operations efficiently, because they're vector processors. They're SIMD processors, single instruction, multiple data. Okay, make sense? So these are the basic requirements to build a vector processor. A vector instruction performs an operation on each element in consecutive cycles, and vector function units are actually pipelined. So each pipeline stage operates on a different data element. Now, if you have a vector whose length is 1,000,000, now you can build a pipeline. That's 1,000,000 stages, right? Now, what do I mean? A vector instruction actually allows deeper pipelines. Why? Because we know that the data elements are independent of each other, right? These are all independent. You're operating on independent elements. So there's no dependency check logic that's required to figure out whether the next element in a vector is dependent on a previous element. By definition, they're independent. So there are no intra-vector dependencies, no hardware interlocking within a vector. As long as you're dealing with large vectors, this is great. Right? There's no control flow within a vector. And known stride, actually knowing this, allows some optimizations that we'll briefly see later on. You can prefetch vectors into the cache or memory. Right? You can figure out what locations you're going to access much before you're going to access it because you know the base address, you know the stride, you know the vector length. The hardware, there could be a hardware engine that goes through this and tries to get the data earlier. Okay, so what are the advantages? No dependencies, enables pipelining and parallelization of these vector operations. You can have very deep pipelines. Each instruction generates a lot of work, assuming you have a nice vector length. Basically, you're amortizing the cost of instruction fetch over many data elements. You fetch one instruction and do lots of things. And we'll see that with an example. You have a regular memory access pattern, and we'll see this also. And you don't need to explicitly code the loops anymore. There are fewer branches in the instruction sequence. Is that clear? So basically, you don't have a loop. You don't. Where is that for loop that I loop? Oh, there you go. That for loop doesn't exist, right? You don't have branches. What you have is the code that I turned into a sequential control flow code here. And this enables you to compact the code even more. Okay, disadvantage. I guess I was going to ask you, but this appeared by itself. Well, there's a big disadvantage, which is works if parallelism is regular. Only maybe too strong, but almost only if you care about performance. If you do not have this regular or data or SIMD, single instruction multiple data like parallelism, then it's very inefficient. For example, what if you're searching for a key in a linked list where the addresses you have no clue about? Actually, this could potentially be parallelized, but there are lots of dependencies here, right, in the linked list. If you have vector operations, on the other hand, this is very, very amenable to vector processing. Actually, this is another paper that we're going to talk about. This is the paper that introduced very long instruction word architectures by Josh Fisher in ISCA 1983. And let's take a look at what he says. And this shows the flexibility of a VLIW machine, but he motivates it this way. To program a vector machine, the compiler or hand coder must make the data structures in the code fit nearly exactly the regular structure built into the hardware, which means that single instruction, multiple data. And data is aligned nicely so that you have strides. And also there's another thing that we will see. Data should be, if you want to fetch multiple loads in the same cycle, those loads, your memory should better deliver those loads in the same cycle, right? Which means that those data should reside in places that can be accessed independently in the same cycle. Which means that somebody needs to lay out that data such that they go to hardware structures that can be accessed independently in the same cycle. What are those hardware structures? Memory banks. And if it turns out the things that you need to access in the same cycle, you're doing a load, and you want to do 6 of those loads on these locations in the same cycle, you'd better have different pieces of memory. Let's say, actually 20 in this case. Let's look at 20. You want to have 20 things supplying different data elements, right? Address 0 should be here, address 6 should be here, address 12 should be here, address 18 should be here, ... Well, if your address 0, address 6, address 12, address 18 are all here, you have a problem, right? You're not going to get all of those data elements at the same time. So that data mapping needs to be regular. And that's what he's saying here. To program a vector machine, the compiler or hand coder must make the data structures in the code fit nearly exactly the regular structure built into the hardware. Well, to be able to do this, you need to know how many banks you have, first of all, right? That's hard to do in the first place, and just as hard to change. Well, what if your machine changes? Right. One tweak, and the low-level code has to be rewritten by a very smart and dedicated programmer who knows the hardware and often the subtleties of the application area. And this actually, if you program GPUs today, this is something you need to do if you want to get high performance. You'd like to be able to have data mapped to different banks such that it can be loaded in parallel for these different vector engines. Okay, so that's the disadvantage, basically. Because you have this regular parallelism that you're trying to exploit, hardware needs to support that parallelism, But not only that, your program needs to fit into the hardware that supports that parallelism. And that's not always easy. I guess before we part, I'll just give you another limitation. Actually, memory can easily become a bottleneck in a vector processor because you have lots of operations generated by one instruction. Think about loading this matrix and a million entry matrix. And one load specifies that, and you need to load it, especially if the compute memory operation balance is not maintained, especially if data is not mapped appropriately to memory banks. If you actually do a bad job in mapping your data to these memory banks, you'll get lots of contention. And there's no easy way to map the data easily, right? Sometimes you want address 0, 6, 12, 18 to be here. But sometimes you want maybe address 0, 1, 2, 3, 4, 5, 6 to be here if you're accessing this way. And these requirements may be contradictory, right? Sometimes you want address 6 to be here. Sometimes you want address 6 to be here, maybe. And you may not be able to. Actually, it's difficult to satisfy both. So that's one of the difficulties in programming these machines, including GPUs. If you want to get very high performance in a GPU, you do need to be able to lay out your data that way. OK, I guess I'll stop here, and we'll continue with vector registers. But we'll have a recitation on Friday. And we're going to take an interrupt, cover virtual memory, because I'll be out of town next week attending the HPCA conference. So save your context. Keep your precise state here. We'll get back to vector processing after we cover virtual memory. OK? But we have a recitation on Friday.